Okay. Hello, everybody. In this lecture, I am going to illustrate to you three different programs. Two of them where we use Python, and the third one we shall use LabVIEW. The first program will find the minimum of the objective function, but the most important here is to show you the positions of the minimum function values beginning from the start point of iteration and ending with the final point where the minimum is obtained. The second program differs from the first one in that it shows the minimum values in motion. In other words, we are going to animate the minimums which we found also along the objective function from the start point up to the optimum value point. In the third program, I shall illustrate with you an interesting program also, where we will optimize one of the functions which we have already optimized in Python, and another two different functions with animation. So let us begin. The first thing to do, as usual, we begin with importing the necessary libraries, modules, and functions. So as you see, we have imported NumPy as NP and imported Matplotlib as PLT. This is what is needed in this program. Secondly, we define our function. It is named function with an argument x, and the function returns x squared minus 6x plus 5. You are familiar with this function. We have found its minimum in many, many different ways. We create an array which represents the range of values representing the x-axis. X is equal, or in another way, from len space function, beginning from 0.9 minus 5 to 8, we have to sample this interval 100 times and assign this array to a variable called x. This x represents the x-axis. We also, as you see here, create an object for the figure object and axis object by using PLT and the function subplots. Directly, when you use subplots, you can create a figure object and axis object together. Okay, now we want to plot our function. So we call the plot function from PLT and pass to this function the array x and the function of this x. They will have the same dimension. Also, within the range which is given above here, we want to limit the axis by setting x limit between 0 and 6 and setting the y limit between -5 and 5. So when you look at the figure here, as you see, this is the range from -5 to 5 and the x range from 0 to 6. From 0, I think, to 6, as I said. Yes. And then we give the statement to show what has been drawn by calling the show function from PLT. At this moment, we can see only this function, which is in color or red color, without these green balls. These green dots or balls represent the instantaneous values beginning from the initial starting point and ending with the point where we find optimum here, and any of them here represents an intermediate value of the minimum of the function until we come to the optimum case. As you see in this figure, there is no motion. There is no animation. This is a static figure here only, but it is really useful and gives an impression how the process is working. So as a beginning, because we want to work with the gradient descent, we will find the derivative of the function. The expression of the derivative is 2x minus 6, assigned to a variable, we call it x derivative. And the function will return the value of the derivative, x derivative, return x derivative, x der derive. Okay, then we create an empty list for the x values, we call it x list, and another list empty also is created for the y values, which we call y list. We will append values to these lists in order to use them to draw the function. For the gradient descent, it requires in advance to give a value for the learning rate. I assume here it is equal to 0.015, which is normal value. The iteration process which takes place here is controlled by using a precision value, not by using the number of iterations. So we assume that the precision of, as you see here, 0.001 is sufficient for us as an accuracy. Of course, we can make the precision smaller to get more accuracy, and maybe we shall illustrate this with you. Now, concerning the x values, the initial value is given or assigned to a 0 value, x previous is assigned a 0 value, and x new is assigned a value half. These are optional values. Now, we begin illustrating the program. We use the while statement. While absolute value of the difference between x new and x previous is more than the precision, this means that the error is comparatively high, so the iterative process must continue. So at first, we change or assign the value of the x new to the x previous. This is the first necessary step. Then we derive or we find a derivative at the point x previous. which is for the first moment equal to 0. We call this derivative dx. As you notice here, we have a sign negative. We could find dx without negation, and we can't do this with negation. This makes no difference. Negation here has a physical meaning, which means that we are going downwards the hill in this direction of the minimum value or the optimum value. After finding the derivative dx, we have to multiply dx by the learning rate. So dx is multiplied by the learning rate. It gives this product. This product now will be subtracted from the x previous in order to get the x new. Because it is negative here, minus minus becomes plus, so x previous plus this product gives the value of x new. Now having the x new, we can append it to the x list here. And in order to find the y list, we find it as a function of x new, which already defined, and append this value to the y list. And that's all. So with these steps now, the gradient descent will continue working and finding the derivatives at each point and examining the difference. And if the absolute value of this difference is more than the precision, so it continues until we come to the point where this value is not more than the precision, less than the precision. Then the program stops. I shall explain to you now why absolute value. And before explaining to you that, what we shall see here, we shall print x new, which means the last value. We shall print x list, the function of x new, and the length of x list. Length of x list gives you the number of iterations which occur until this inequality is not real. So this is the length or the number of iterations which happens. Now, when we run the program, we have got this figure with these values representing the minimum values at each iteration, at the first iteration, the second, the third, the fourth. Here, the last iteration or the last part of this curve is not seen because the difference between the value of the minimum and the previous value of the minimum becomes very small and very close to 0.1, 0.001, which was given as a condition here by us. The difference becomes very close to this value, and so we cannot see it separately. They are overlapping on each other here. This means that the number of iterations which I am working with is more than necessary, and but really I am not controlling the process here by the number of iterations, so it happens normally. So the local minimum occurs at the x value, which is 2 0.967. This is the X value, X new. Remember, in previous lectures, it was found 3. It is about 3. There is a little bit difference here. I can explain to you how to work with it. All these minimum values of these dots, which represent the minimum values, are given here also as a list. And the last value should be the same value as we have seen, 2.967. This is the last value which is given here as the same. But here we can read it only from the list. And the number of iterations, which is the length, as I said to you, is 143 iterations. So it took 143 iterations until we achieve the accuracy which was required. Suppose we want more accuracy. Of course, this means that we need more iterations. Suppose we need more, and instead of 0.1, let us put another 0, like this. Now the accuracy is very high. So if we run the program again, the number of values will become more, as you see here. This list has a higher number of values, and the number of iterations now 219 instead 140. This is necessary in order to achieve the required accuracy. So this depends on what is needed. Now let us come back and also look at the initial value which I have suggested for the X new, the intermediate value. This is the X previous, this is the new. I have suggested to begin with X equal 0.5. 0.5 here. Here is 1, here is 0.5. We are beginning from this point with an X equal to this value. Suppose that we want to work with a value from other side, 5.5. The range here begins from 0 up to 6. Why not to work this way to find the minimum, and to begin from this side instead of this side? Let us try. If we put there 5, and I selected 5.5 so as to be in this region, and that you see the point here. So if it is given 5.5, for example, and now we run the program, as you see, the program runs perfectly, beginning from this point and continuing at the same minimum here, and it will give you the same number, about the same number of iterations, 219. I have forgotten how much they were in the previous case. Very near to that. Now, why it is working from the right side or the left side correctly? This is because we are working with the absolute difference. We are working here with the absolute difference between both. If I take the function absolute, and work with while X new is more than X previous, look, if I am working at this point here, the new point will be to the left. The X previous will be more than the X previous will be more than the X new. So if I run the program now, only I get an answer for the first point. It doesn't work. It works only from this side. If I now instead of 5.5, give an initial value of half only, as I did before. Here, now half, and I run it, it will run. Why? Because the next value is always here less, the next value of x is always higher than the previous value. So it continues working and normal without absolute. So absolute value here is interesting for you and gives you facility to minimize the function beginning from the left limb from this side here or from the right side here, and you will get exactly the same answer. Yeah. I think this is the most interesting here of this program. So again, here we have revised together the principle of gradient descent, and we have stopped the program by using inequality condition with a given value of tolerance, and we have used the function absolute, which gives this facility to optimize from either side of the function. Okay, we have finished with this program. Let us move to the second program. The second program is the same, or let me say, is for the same function. But we will not look at all the points at one time. We will see how the point of minimum is moving from the starting point to the ending point where the minimum occurs. And we shall see that this point really, which moves selectable. We ask the program to give or to show every 18 iterations 1 point, after another iterations 1 point moving, one movement of these particles. Okay, let us see what is going to happen there. So in order to realize this, as you see in this program, we need to use a function which is called FuncAnimation. FuncAnimation is a class, really. It is not a function, which is included in the animation sub library. And this FuncAnimation, in order to work, it requires to pass, this is its syntax, it requires to pass several arguments. The first one should be the figure which we have created, and the second one should be the function which updates the data of the object which is going to be animated, and the third one is the initial value, the initial state of the object which is going to be animated, and then it requires the number of frames which we want to work with, and the interval or interval between a frame and another frame. And also it requires an argument called blit to be true or to be false, depending on whether we want to show that part of the function which has changed or we do not want to show it. So here blit is equal to true because we want to show it. So let us begin our work now, considering what I have said. So we must import all the necessary libraries and functions and classes relative to our program. we import numpy as NP. It is necessary because here we are going to create an array, so numpy is necessary. We imported Matplotlib as PLT because we are going to draw and animate. And animation is part of Matplotlib. So if we import Matplotlib and call from Matplotlib the animation module as animation, and from animation also we import the FuncAnimation class. And the third or the last, let me say, we, as you see, from IPython import IPython display, we import HTML viewer. This is necessary in order to view inline in the notebook, because I am working with a notebook, in order to view the displayed plot. Now, after importing what is needed, we begin our work. So we create the object X. Now you know what is it, but it is now, it now has a difference range from -15 to 21, from -15 from here to 21. This is the same function which we have worked with in the previous lecture, in the previous example, but with another range from -15 to 20, with I don't know how many samples there, with about 100 samples. And this is the expression of y as a function of x. We create an object here and called initial minimum value and the temporary minimum value. This is the same as x previous and x next. No difference, different only in the writing or in the way of expression. So the initial value, which we will work with, is called initial minimum, and this is the initial value, and the temporary value which we will work with is given or assigned a value equal to 18. We assigned number 18 to the temporary, or new in another way, minimum. So the value of 18 will be around here in this area, about 18, and here it is, its ordinate will be here. Okay, so this is just an assignment values. We shall try another values later. Let me just give you an idea first about the program. Also, the step size here, or the learning rate, is equal to .15. The precision is given 1,000. We define the derivative ft called, instead of derive, fd given another name, and it has the same expression, of course. And here we have created a list, an empty list, and assigned it to an object called minimums, mins, M-I-N-S. Now we have assigned this list to this variable, which is called minimums, to this object. And now, as again, while absolute value of temporary minimum minus initial minimum, this is the 0 value, and this is the 18 value. When it is more than the precision, which is given 1,000, then first of all, we have to assign the temporary minimum to the initial minimum. Then we will find the gradient fd of the initial value, initial minimum. We call this gradient gradient. We gave it the name gradient. This gradient is multiplied by the step size, which is the learning rate, the same thing. The gradient multiplied by the step size or by the learning rate is given a variable called move. And this move will be subtracted from the initial value to get the temporary value. Having the temporary value, we now append it to the minimums list here. So as you see, this sequence of operations is the same as we did in the previous example, nothing new. We are just creating using gradient descent and finding the values of minimums, and these minimum values are stored in the list. We ask the program to round the temporary minimum to 3 digits. This is not compulsory, but because the numbers are very long, so as you see here, they are very long here, as you see. We do not need them. I asked to find them with approximation to 3 digits, 1 digit, 2 digit, 3 digits only, just to show you that this may happen, may be needed. This is the minimum value, and we print the minimum value then after rounding it. We call it minimum value, and this temporary minimum, we call it minimum value, and this minimum value now is printed. In Python also, we can print the final value as follows: print minimum values minus of -1. This means the last value in this list, the last value in this list, which is here now, 3.0319. Here it will be given, this value. So of -1 means the last value. Of course, you can write -3, you will get the last 3 values, or -5, the last 5 values, as you want. So I have just wanted to show you how we can get the same value differently. If I write print minimum values, we shall have all the values together. So here means is this list, which includes all these 220 values, 202 values, which really as a result of 202 iterations. Also, up to now, I think nothing new. Length of minimums is 202. So up to now, nothing is new to you. This is repetition to the previous example without working with the animation. Now we shall work with the animation. So as you see, the figure, the function FuncAnimation requires a figure to be created. So at first, we through PLT call the function figure. We assign to this figure a size, for example, and gave it the name fig. Now this fig is already created. So we create a figure object. What is this fig? This is the frame or the window which shows up when we run the program by printing PLT show. Also, we create the axis. This is the area where the plot going to be, PLT axis, and with limited values of x and y. So the x limit we gave between -15 and 20, the y between -15 and 250. If you look at the figure there, it will be -15 and 250. Here, -15 and 20. These are the limits of the figure which we will work on. So at this moment, we have assigned a figure, and this figure will be passed to the function animation or FuncAnimation. A first step to do is to plot x, y function, the basic function, which is in blue here. It is drawn, as you see here. I have drawn it by this statement. This is the drawing representing our plot, which we will work on. Now, to work with animation, we usually require two functions to define: the initiating function and the updating function. The initiating function, the most important thing here is you create the object which you are going to animate. In our case, it is a line, and assign data for this line equal to 0. In other words, assign nothing, it is empty. So line dot set data, this is a function set data, to lists empty. Why they are empty? Because these empty lists will be filled by the update function later on. And the other important thing with this initial function is to always return the object which you are going to animate. Here we are going to animate the line, so return the line. That's it. Now we have finished with the initial function, nothing difficult here. Now we come to the update. The update function is defined in this manner: define update, and the argument here is I, or sometimes it is called in, or sometimes it is called underscore. Any symbol you want, you put it here. It is not more than a variable which represents here iteration index. Sometimes many people write frame instead of I, which means from frame number 0 up to frame number so and so. So this function now is created. Inside this function, the minimum, this is the list, minimums list, which we have created here, minimums list, which we have there. Yes, it is filled with 3 sections: start, stop, and step for each iteration. And this is given a name called xn. So this is the value of the x coordinate. What is 18 here? 18 means here that for every iteration, for every 18th, it is a step, it is a jump, like that. If for every 18 iterations, we shall see only 1 point on the figure. You understand that? Having this xn now, we can find yn as a function of xn. So yn is xn squared. This is the function here. It is squared, sorry, it is here squared, minus 6 multiplied by xn, minus 6 multiplied by xn plus 5. So now we have xn and yn, and now we need to update to fill these empty lists with these values. So we say line set data. Which data we want to set to this line? xn and yn. Every xn and yn for every I here must be put inside these 2 lists. And at the end, we return the line. Here, the update function is now complete. What is left? Nothing, except to use the class of FuncAnimation. Okay, so line here, AX plot, this we have done here before, but this is done for you for another purpose. This is the line which is drawn as when we call the AX dot plot function, as it is here. Yes, line, but We did nothing. We did not give anything inside. It is empty line, but we have added asterisks with a color red and call it markers, which is with a size equal to 8. This is the this is the point or the asterisk or the thing which will show the position of the minimum when it moves. It will move on the plot now, which is empty. Because it is empty and you will see only it over the original one which has been drawn. I have written a special statement here. Length of minimums starting from 0 and ending with all the values with a step equal to 18. I gave it the name frames. So in the FuncAnimation function here, frames equal frames. Figure is the same as figure there. Update is the same as update here. Initiate is an initiate function. In the syntax of this function, it is given a name initiate function. So initiate here, this initiate is assigned to initiate function. So now we have passed the most important arguments, the figure, the update function, the initiate functions, the frames as the number of frames. Of course, you can here, instead of frames, you can write 100 and it will work. No problem. And the interval between frames is given 300, here 300 milliseconds. And the split function is true because we want to see this animation. This animation is given a variable named anim or any. Some people write anim, some people write ani. You can write anything you want. Now we want to save this anim, so we call the save anim. We call the save function. We give the name of the saved file as rasmi.gif. The type of this file will be GIF. And we shall use the writer ImageMagick as we did before. And now we ask PLT to show all this material. After that, because I am working with notebook, as I told you, I use this instruction in order to see in line in this page the plot which has been already drawn. And the most interesting here that this plot could be seen upon request. I can see it anytime I want without running the program. This is an advantage here. So, of course, if we run the program now, it will take some time. This time I want you to see it. Maybe it will take 1 minute or 2 minutes. Let us run the program and see what is going there. As you see, some part of the program is already has been shown, but the animation itself takes time. The animation process takes time, so we shall wait. And now this function appeared, and the other function appeared. This plot, which is appeared as a result of the HTMLI viewer. This part is appeared as a result of the animation function here. If I go now also to an address called rasmi.gf, I shall see there the same figure. Let us try and see what is going there. Rasmi, I think Rasmi, where it is, rasmi.gif. Okay, so we go here and write rasmi.gif. Here it is. Let us go and see where it is. Here it is. Now I run it. Here it is. Now it is in motion, as you see. Now, every 15 iterations, it shows a position. And the number of positions, I'll talk with you about it. I didn't really explain it to you. I'm sorry, I've gone out of it. Now I shall retrieve it back. This is not my file. I'm sorry. My file is this one. Okay. This is the first example. This is the example I am working with. Here are the values of the minimums. Here is the first drawing, and here is the second animated one. As you see here, the point now is against 18 here, and it is stationary. If I run the program here, it will move and show you the trajectory. And if it is here pointed as loop, it will continue doing that continuously. If you want to stop it, you can stop it at any moment of time you want. If you want to run it for one time, you can run it for one time also. You have to give a chance to go back. Yes. For example, here, and I run it once, it will continue until the end. Okay. Now, what else? What information I have got? I should see, or there is nothing about it. Yes, it is. Number of iterations here, 202. So the number of iterations which took place, 202. What is the number of points, which is this asterisk? How many times it is shown up while moving from the start point to the minimum? The number of points will be equal to 202 divided by 18. It is not given by me. I didn't do it, it seems to me, for you. But it must be equal 202 divided by 18. Oh, yes, here it is. Frames number 12. What I have done there, print frames number, which is equal to frame, because the frames is equal to the length of minimum values which exist in this list. So I know the frames, the length of them, I know them, so they represent the values of asterisks which move there. And another way, really, how many they are given here? 12. Another way, if you go and divide 202 by 18, you will get the answer also very close to this, which is about 11.33. It is approximated as 12 frames. You cannot divide the frame. So if you change the steps in the list, for example, from 18, let me say to 10. Here is 10 now. Of course, I have to change it also here, or it is sufficient there, I think. Now, if I run the program, there are 202 iterations divided by 10, it will be about 20. If you run the program, newly, you have to run a newly. It is not shown yet. Or yes, no, it should change. Override. It is not taken. Let me, yes, it is taken here. I should change it here also to 10. It is included here. Now, let me look if there is a need to change anything more. It is changed here. It is changed here. And yes, at the same beginning here, it should be also 10. And now, if we run the program newly, this is the bad thing of animation, as you see, is that it takes time. Sometimes it takes 5 minutes, sometimes it takes 3 minutes, sometimes it takes more than 5 minutes. So, but really, animation itself is very interesting and gives you an insight to the program and how the things are done and how they are moving. As you have seen in the previous lecture, for example, when we worked with the pie swarms and how the pie swarms are changing their positions and how they collide together in a given point, which is the optimum point. Here, the number of iterations is 100, not yet, 177, and the number of frames is 18. You see? It is 18 and not that value as before. Okay. Of course, the basics for that also, you can see 177 divided by 10, which I have included, it will give you about 17.7, which is 18. So it is here 18. This is the interesting thing. Secondly, or lastly, let me say, what I want to illustrate with you. Here, the temporary value, I took it 10. Here I am working with the absolute value, as I have explained before. So it doesn't matter if I take, instead of 10, minus 13, for example. Of course, I can take minus 10, not minus 10, not minus 13, and run the program. Now the motion will be from the other side. The motion now will be from left to the right side. But the values will be the same, 20, and the minimum value of the program will be about, as you see, about 329, 2.964. And of course, the value of the function is -4 is well known to us, and I am not trying to repeat it. So as you see, it is now from the right side, and if I run it here, it moves from the left to the right, not from right to left. This is why, because I am using the absolute value, and I can work with the positive side or the negative side. Okay, so I think with animation, with Python, for single variable, it is sufficient. Now, let me move and explain to you and demonstrate with you how we can work with LabVIEW. I have put all the programs for optimizing in LabVIEW in one folder. I'll illustrate with you this example today. This example works by using a function in LabVIEW which is called Global Optimization VI. Global, so in other words, as you see, this function here, it is global optimization. This function, as you see, finds for you only the global value, the global minimum. It doesn't find the local minimum. But if the local minimum is the global one, it is the only one in the figure, in the plot, so it gives you the answer, of course. But if you have more than local and one global, this gives you the optimum of the global minimum. Let me give you some information about this program, and then I will illustrate with you 3 different functions working with it. Some of them is familiar to you. First of all, this VI or function here works, as you see, with this input here, objective and constant function called, but this function really is called from another program. And this is the main program which we have here. We shall have an additional program where we have already established the objective function. And this main program calls the objective function which is in the other program, or sub VI or VI program. The interesting thing here, and the reason for that, is the objective function itself does not exist in the memory of the computer now. It is just given as a file, and when this main program calls the objective function is loaded, then executed, and when this program stops, it will be taken away from the memory. This is just to improve the memory size of the computers. So this element here has a name called, it seems I have Open VI reference. Really, it is here. You can go and find it from the application control here, the Open VI reference. And from this Open VI reference, you can create here an objective and constraint figure which represents the terminals, inputs and outputs which are related to the objective function. And the objective function itself is here in this program. Here is the front panel, and here is the block diagram. Here I have 3 functions. This is one function. It is not connected to the output. This is another function not connected to the output. And this is the 3rd function which is connected to the output. The output here is through an array. It is called objective function. What is this function? This function is the Rosenbrock function. You remember this function. 1 minus x squared plus y minus, this is x. The first input is x. The second input represents y. So this is, as you see, 1 minus x squared, or x minus 1 squared. It is the same. There is no difference between them. And this is added to y. This is y minus x. Both are squared, as you see here, and then added to the above. This is Rosenbrock. You remember when we worked with Rosenbrock, we found that Rosenbrock has, because it is two variable function, it has an x and y values which represent the point where there is a minimum, and it has one minimum which is equal to 0. If we run the program now, let us run the program. You will see these are the particles, and they are changing by time, and they are colliding together at this point, which represents the optimum coordinate where the optimum value of the function occurs. I have intentionally given the while loop there a time delay in order you can see it slowly. But as you see here, x, this is the coordinate x, this is the coordinate y. The value at optimum is when x equal to 1. This is 1, this is 2, this is 3. So it is x is 1 and y is 1, as you see. And the value of the function, you remember, it was 0. So as you see here, x is 1 again given for you, y is 1 given for you, and the value of the function, which is minimum 3.09 to the exponent of -8, which means 0. So as you see, it works very nice. It gives you the minimum of Rosenbrock directly without any problem. Suppose we want to find the minimum of the function which we have just worked with, which is x squared minus 6x plus 5. Here it is. This is x. This is x squared minus 6 multiplied by the same x plus 5. Now, what I have to do, I have to disconnect this output and connect it with the output here. And now we shall find the minimum of this function. But as you remember, this function has only one variable x. There's no xy. So it will give me only the optimum at the value of x. And of course, the value of the optimum, which is -4. Okay, let us go and try to run it. Now, save changes. Yes, and I want to run the program to other function and see what is going to happen. Look, all the particles now are aligned with the 3 value, which means they all have a coordinate equal x to 3. This is the optimum value, the optimal position x of the function. And here it is given in a written form, 3. You have got another figure here. This figure is untrue. You can ignore it. But you are given also the best minimum, which is -4, as we did before. So it works perfectly and there is no problem. Okay, let us try another interesting example. It seems to me I have gone out of it. No problem. I shall be back. Until that occurs, let me show you one thing. Jupyter Notebook Classic, enter. I have opened the Python programs again to show you or to remind you with an example which we have worked with 2 lectures ago. And now I shall use LabVIEW to solve this problem newly with animation. With animation, yes. Okay. Let me go down and find it for you, just to remind you with it, is what is there. Where it is. Here it is. Remember this figure. This figure or plot has two minimums. This is a global minimum, and this is a local minimum. The function we are working with only detects the global minimum. The global minimum of this function was found as -177. This is the value of the function at minimum, minus, and the value of the x coordinate is -0.45. These are the findings when we worked with Python. Now let us work with the same function and now let us go to LabVIEW to see our function. We go and open the block diagram. We open the page where we have written our objective functions. Here is the function which we are interested with. This function is x squared plus the sine of pi multiplied by x, and this sign is multiplied by 2 and added to x squared. This is the same function which has been there, only given in LabVIEW terms. Now we open this and connect the output to this function and go out and run the program. Save. Now the answer should be -177 and -0.45. Go and run. Look, the best minimum -177. The coordinate minimum value -0.45. And here is -3, as you see. Here is x equal to 0, here 3, here -3. Here is the value which represents -0.4555, about in the half. All the values are at this value because we have only one variable, which is x. So as you see, this function really is not bad. It is very excellent, but it only detects the, let me say, the global minimum, and it doesn't detect the local minimums, which is really, of course, a problem. Now, I have forgotten to give you some information regarding this function. So as you know, I have said to you that this function works by calling the sub-VI or the VI of interest by using this arrangement here. It requires from you to give a beginning state for the swarms. I have managed, and really the author managed also to give them 0 value, and the initial values are 0. So you did nothing, only you create this terminal. You give the bounds of the function. I have given the bounds between -3 and 3 and 5, it depends, but all these values really are adequate for all the 3 programs which I have run with you, because x was always equal to 3 or equal to 1, and so no problem. So they are included within this range. This is the array, a cluster of arrays, which represents the bounds on the x and y. Here is the outputs, the minimum value, the coordinates of the minimum, and the value of the function, which is the minimum. Here, you just need, even you may not connect, but I have really connected it previously. You have just to connect these 2 inputs, just they are not needed to work with. Here, as you see, the output is as a cluster. I have used to unbundle function by name to take the pi swarms out and to display the pi swarms. Here, the population really means this place where you display the pi swarms. They are not Python swarms, the swarms in general. Yes. Now, if you go back to the function also, save, for example. Anyhow, I am going out of it twice wrongly, but I will finish just now. I have just wanted to show you how I made the delay in order for you to see slowly how the particles are colliding and moving towards the minimum value. If we go here, and let me show you, sorry, not this one here. Okay, I'll connect with the I'll disconnect from here and connect it with the Rosenbrock function. And now go back, save. And now let us go to this is the block diagram. Here I have included 1000 milliseconds, and it means 1 second delay between iteration and another iteration. You have noticed when I displayed the function here, you have seen these are the particles and how they are moving slowly, slowly, and colliding until at the end they all collide in at the coordinate 1 and 1, which is here, no 1 and 1. Yes, that's true, but really, this is a good way. But if I decrease, this is from 1000 to, for example, 10, you will see how very quickly the algorithm is very powerful, that they collide very quickly and very easy without that time. Look, and that's it. I run it. and that's it. When, the coordinates, and the value itself is given here as a 0 because it is 0. Okay, I think this is sufficient for you today. I hope that this was also very useful. We have learned, I think, very interesting things. How to show the minimum values in a static form as non-movable points on the same objective function. How we can realize the movement on steps by dividing the list to a given steps in order to have a limited number of iterations. How to use LabVIEW also to find the global function animation and for other functions which I have demonstrated to you. Thank you very much for listening. I hope that everything is okay. I am wishing you the best and goodbye.